Hello students. In this lecture, I am going to start particle physics. In particle physics, first I am going to discuss the fundamental interactions. There are four types of fundamental interactions: gravitational interaction, electromagnetic interaction, then weak interaction and strong interaction. One by one, I will discuss all these four interactions. So basically, first question is, what is the meaning of fundamental interaction? So fundamental interaction are the ways in which individual particles interact with each other. So fundamental interactions are the ways. Fundamental interactions are the ways in which individual particles interact with each other. There are four types of fundamental interaction. First is gravitational interaction. Second is electromagnetic interaction. Third is weak interaction. And number four is strong interaction. So these are four types of interactions which can take place in between individual particles. So first we are going to start with gravitational interaction. So first interaction is gravitational interaction. This is the weakest. This gravitational interaction is weakest of all the fundamental interaction. So this gravitational interaction is the weakest interaction out of these four interactions. This gravitational interaction is the weakest interaction out of these four interactions. It takes place, or it acts in between all bodies. It will act. This gravitational interaction takes place in between bodies having masses. This is a long range interaction. Or you can say that the range of this interaction is infinite. You can take these particles in between which this interaction is taking place. You can take them very far away from each other. Basically, the amplitude of interaction or the force that is acting in between them, that will decrease. That is surely going to be decreased, but still there will be some force. So this is a long range force in between them that is acting. So in between them long range interaction takes place. So this gravitational interaction is long range interaction, and it is governed by inverse, it is governed by inverse square law. And this law is the force between two bodies having masses is given by, this is a gravitational constant. Suppose mass of the first body is m1, mass of the second body is m2 divided by r square. So here this F is proportional to 1 upon r square. That's why this is known as inverse square law. This is known as inverse square law. Basically, what is the reason or what is the cause of this interaction? Suppose we have two particles which have masses, then in between these masses, this interaction is taking place due to the exchange of a quanta that is known as graviton. So basically, this interaction is taking place due to the exchange particle. Due to the exchange of the particle that is known as graviton. This is the quanta of interaction. So basically the interaction is believed to be mediated through the quantum of interaction that is known as graviton. Basically this type of interaction is very important if you are talking about the forces that is acting between planets. If you talk about the interaction that is taking between planets or the earth or these planets, they are exerting gravitational force on other bodies. They are basically attracting other bodies due to this gravitational force. All these type of interactions, they are covered under the purview of this gravitational interaction. If you want to represent this interaction between these two particles, then how will you represent this? Suppose this is first particle, this is first particle, this is second particle, this is second particle. They are having masses, then they interact through the graviton. They will interact through the graviton. So we can represent this type of interaction like this. We can represent the gravitational interaction like this. This is the way to represent the gravitational interaction. The interaction potential between two particles have the following form. If you write down the form of gravitational interaction, VGR, suppose this is, so this will be how much? This will be G, M1, M2 upon R. This will be the form. But if suppose we try to find out the gravitational potential between two protons, then this will be Gm mp square upon R. So basically this is the gravitational potential or interaction potential between two protons. So this is the form of gravitational potential. So you can write down the gravitational interaction potential has this type of form. So this is the form of gravitational potential. Apart from this, this type of interaction is represented by a characteristic dimensionless constant. It is represented by a characteristic dimensionless constant. Which represent, or you can say constant representing representing the strength of interaction. Strength of interaction. This is also important. This is an important parameter which represents the strength of this gravitational interaction. This is given by G. This constant is given by G mp square upon h cross c, and its value is 6 into 10 to the power minus 39. So basically this constant is used to represent the strength of interaction. This is known as characteristic dimensionless constant for the gravitational interaction. So this is first type of interaction. This is weakest of all interaction. It takes place between two bodies having masses, and this is governed by inverse square rule, which is given by F equal to G m1 m2 upon r square, and very similar to the electromagnetic interaction, which is intermediated or which is mediated by photons. In a similar fashion, this gravitational interaction between two particles having masses, this is mediated through gravitons. And the gravitational interaction potential has this type of form: VGR equal to G m1 m2 upon r. If you represent the gravitational potential in between two protons, then this will be G times mp square upon r. And this is an important parameter, G mp square upon h cross c. This represents the strength of interaction, and its value is 6 into 10 to the power minus 39. 6 into 10 to the power minus 39. If you talk about the characteristic time on which this interaction takes place, that is 10 to the power 16 second. If you want to write down the characteristic time then characteristic time is of the order of 10 to the power 16 second. So this is the time scale on which this interaction takes place. Apart from this, if you want to know about this graviton, so its spin and parity is, always remember that here, that its spin is 2 and parity is positive. For this particle, spin and parity is 2 plus. These are long range interactions, so these are almost I have discussed every important aspect of gravitational interaction. Another important thing about this gravitational interaction, that when you are dealing with elementary particles, or the interaction between proton and proton, in between neutrons, basically interaction between these nucleons, or interaction of electron with nuclei, or this type of, if you are dealing with particles which have very, very small masses, then we can neglect this. Or you can say this interaction will be negligible in that case when the interaction is taking between two particles having very small masses. So here, when we will deal with this particle physics, basically we are going to ignore this type of interaction. We are not going to, or you can say this type of interaction will not be very important. This type of interaction will not be very important. Now come to second type of interaction, electromagnetic interaction. So second type of interaction is electromagnetic interaction. Number 2. So we have discussed this one. Now come to second, electromagnetic interaction. This type of interaction. So this type of interaction takes place between charged particles. So first important aspect about this interaction is it takes place in between charge particles. So this is first important, charge particles. So this is the first important property of this type of interaction. Second important interaction is this is also the long range interaction. Very similar to gravitational interaction, it is a long range interaction. Long range interaction, and it is governed by Coulomb's law. It is governed by Coulomb's law, which is also the inverse, which also follows inverse square law, So basically it is based on inverse square law, and due to this reason this is a long range interaction. So form of interaction is represented by this Coulomb law, and this is given by 1/4 pi epsilon naught Q1 Q2 upon R square. So here this F is proportional to 1/R square. So this is a long range force and it is following inverse square law. It is inverse law. Another important thing, next point is it is stronger. This electromagnetic interaction is stronger than gravitational interaction. Gravitational interaction here is stronger than gravitational interaction. Now next question is how this interaction is taking place. As in case of gravitational interaction was taking place due to the exchange of gravitons. In a similar way, basically this type of interaction between charged particles is taking place due to the exchange of photons. So what is the exchange particle here? Here exchange particle is photons. Here exchange particles are photons. Or you can say that this type of interaction is mediated by the photon. What is the characteristic time, or on what time scale this type of interaction takes place? That is 10⁻⁻20 seconds. So what is the characteristic time? For this interaction? Characteristic time is of the order of 10⁻⁻20 seconds. So this is the time scale on which this interaction takes place. So this interaction takes place on the time scale of 10⁻⁻20 seconds. What is the spin and parity of these photons? For photons, if you want to write down the spin and parity, spin is 1 and parity is negative, odd parity. So these photons are odd parity particles with spin 1. If you want to represent this type of interaction between two electrons, then how can you represent this? This is an electron. This is another electron. So these two electrons, they will interact through the exchange of photons. Exchange of photon like this, and this type of interaction is represented by this type of figure. So this is the way to represent this electromagnetic interaction that can take place between two electrons. As far as the form of the potential is concerned, form of potential will be like this. If you talk about this electromagnetic interaction, then for this interaction, basically form of potential is like this: 1 upon 4 pi epsilon naught. This will be Q1 Q2 by R. If you are talking about the interaction between two electrons, then it will be E square upon R. So interaction, basically potential corresponding to electromagnetic interaction will have this type of form. Another most important feature is, what is the characteristic dimensionless constant? Here this is G point. Another is characteristic dimensionless constant representing the strength of the interaction. Here, this is known as fine structure coefficient. Here, this constant is named as fine structure constant. Its expression is E square upon 4 pi epsilon naught H cross C, and its value is 1 upon 137. So this is the field strength. If you want to represent the strength of the interaction, then for this characteristic dimensionless constant will be fine structure constant, whose value is equal to 1 upon 137. So these are all important aspects about the second type of interaction, that is known as electromagnetic interaction. The next type of interaction is weak interaction. So we have discussed first two interaction, and next interaction is weak interaction. Third is weak interaction. This weak interaction is the fundamental interaction that takes place between leptons and hadrons. So basically this is a fundamental interaction that involves leptons and hadrons. So this is one of the important fundamental interactions, and important property is that it involves leptons and hadrons. This weak interaction involves leptons and hadrons. The most important example of this interaction is beta decay. If you write down the important example, then one of the important example is beta decay. And second, another important example is decay of strange particles. This interaction takes place due to the exchange of W plus minus bosons and Z naught boson. So basically here, in this case of interaction, exchange particles are W plus minus boson and Z naught bosons. These are heavy bosons. This W plus minus and Z naught, they are heavy bosons, and due to this reason they are short range forces. Because they are heavy bosons, as they are heavy bosons, so you can say, as this interaction is mediated through these heavy bosons, so due to this reason they are short range interaction. So this weak interaction is short range interaction. Short range interaction. Its interaction range is roughly of the order of 10 to the power minus 18 meter. This is short range. This is a short range interaction, and its range is roughly 10 to the power minus 18 meter, and corresponding characteristic time is 10 to the power minus 10 second. Because short range is very small, so corresponding to this characteristic time is of the order of 10 to the power minus 10 second. So because they are mediated through heavy bosons, so due to this reason they are short range forces. Their ranges are of the order of 10 to the power minus 18 meter, and their characteristic time is 10 to the power minus 10 second. And even in case of weak interaction, another important thing is that in weak interactions, the strangeness quantum number, here another important property is, in case of weak interaction, strangeness quantum number and charge conjugation are not conserved. Even in case of beta decay, parity is violated. So parity may be violated in case of weak interaction, and example is beta decay. So here, in case of this weak interaction, parity may be violated. For example, in beta decay. How can you represent this type of weak interaction? So for this, suppose this neutron, this is a neutron here, this is decaying into a proton. Then in this process, a W boson will be involved, and this W boson will decay into electron and an antineutrino. So we can represent this weak interaction like this. So in this way, this weak interaction can be represented. The form of potential corresponding to weak interaction is like this. Weak interaction. This is G, some constant. This is GW. This is GW by R exponential minus R upon RW. Here this Rw is the range corresponding to W bosons, heavy bosons, and this Rw is roughly equal to, it will be H cross by 2 mass of these W particles into C. So this is the form of the potential. This is the form of potential corresponding to weak interaction. If you talk about the dimensionless constant, or you can say characteristic, if you talk about characteristic dimension constant, dimensionless constant representing the field strength, then it will be equal to GF into mp square C upon H cross cube. mp square, mp is the mass of the proton, and this will be roughly, if you calculate this value, this will be 10 to the power minus 5. So this is the characteristic constant. This is the characteristic dimensionless constant which represents the field strength of the interaction. Field strength of the interaction. Now what is this GF? Here, what is this GF? You have studied this GF in case of beta decay. This GF is known as Fermi coupling constant. Fermi coupling constant for the beta decay. This GF is Fermi coupling constant. This is known as Fermi coupling constant for beta decay. In beta decay, when we were discussing Fermi theory of beta decay, we have learned how can you calculate the value of GF. Its value is 1.4 into 10 to the power minus 49. Its value is 1.4 into 10 to the power minus 49. This will be in erg centimeter cube. This will be erg centimeter cube. This will be the unit. So these are all important aspects of the weak interaction. So weak interactions are short range interaction, and this type of interaction is mediated by heavy bosons like this. Next type of interaction is strong interaction. So next interaction is strong interaction. Strong interaction is the strongest interaction that is present in the nature. It has the maximum strength of interaction. This is the strongest interaction present in the nature. So next type of interaction, 4 type of interactions is strong interaction. Strong interaction. So this type of interaction is the strongest among all these four type of interaction. It is strongest interaction that takes place in between proton and proton. It takes place in between proton and neutrons. It takes place between neutrons and neutrons. It involves mesons and hadrons. It also involves mesons and hadrons. So how this type of interaction takes place? How this type of strong interaction takes place? Basically, nuclear forces that are acting inside the nuclei, they are the examples of the strong interaction. So this type of interaction takes place due to the exchange of pi mesons. So here exchange particles are pi mesons, so pi plus, pi minus and pi naught. So basically exchange particles, so this type of interaction is mediated by pi mesons. But later on it was found out that these protons, neutrons, mesons, hadrons, they are made up of quarks. So these protons, neutrons, mesons, hadrons, they are made up of quarks. So one can understand the strong interaction. One can understand that actually strong interaction is taking place in between quarks. So due to this, one can assume that strong interaction is taking place in between quarks, and the mediating particle or exchange particle is gluons. And exchange particles between quarks, due to the exchange of this gluon, or you can say the mediating particle in case of strong interaction is gluons. So here mediating or exchange particle in between these quarks, in between which strong interaction is taking place, they are gluons. These strong interactions are also short range forces. In case of a strong interaction, this R is roughly 10 power minus 15 meter. Range is of the order of 10 power minus 15 meter. And characteristic time of interaction is 10 power minus 23 seconds. That is very small. So here characteristic time is of the order of 10 to the power minus 23. So they are taking place, this type of interaction, this type of exchange of these particles is taking place at the time scale of 10 to the power minus 23 second. This is second. 23 second. How can you represent this type of interaction? So for this type of interaction can be represented like this. This is blue quark. Suppose this is red quark. And these quarks, they interact through gluons. through gluons. They interact through gluons. So we can represent the interaction between these quarks like this. As far as the potential of this interaction is concerned, its shape is like this. For a strong interaction, the shape of the potential is GH upon R. This is exponential minus R upon R. This R is the range, and value of R is H cross upon M pi C. M pi C. This is known as the This is also known as the Compton wavelength of pion. This is also known as Compton wavelength of pion. Compton wavelength of pion. Here, due to this, this is exponential term, exponentially decaying term is present, and from this term we can also explain the short range nature of this type of interaction. So due to this exponential term, e to the power minus r by r term, these strong interactions are short range forces. As far as characteristic constant characteristic dimensionless constant representing the strength of interaction is concerned, it is GH square upon H cross C. So in this case, this characteristic dimensionless constant alpha s is given by GH square upon H cross C, and its value is nearly 1. So these are all important aspects that is required to know before starting the discussion of elementary particles, and later on when we will discuss other aspect of these elementary particle interaction, then these points will be very important. So I have discussed most of the points which are necessary for the discussion of the elementary particles. So here in this lecture I have discussed with you people all 4 types of interactions: gravitational interaction, electromagnetic interaction, weak interaction, and strong interaction. Now here in the last, I want to summarize the properties of these 4 types of interaction in a table. So here now I want to summarize all the important parameters related to these interaction in one table. So first is basically here, in the first column we will have interactions. So first interaction is suppose strong interaction, electromagnetic, second interaction, then weak interaction, and number 4 is gravitational interaction. If first I want to summarize the relative strength of these interaction. Relative strengths. Here we are considering the strength of strong type of interaction as 1. Then the relative strength of electromagnetic will be 10 to the power minus 3. This will be 10 to the power minus 5. And this will be 10 to the power minus 40. So these are the relative strengths of these 4 type of interaction. Next is range. Range of these interactions in meter. So this will be range for strong interaction is 10 to the power minus 15 meter. This is infinite range for electromagnetic forces are infinite. For weak interaction this is 10 to the power minus 18 meter, and again this is infinite. This is infinite. Next is characteristic time. Characteristic time. So characteristic time in second. This is 10 to the power minus 23 second. This is 10 to the power minus 20 second. This is roughly 10 to the power minus 10 second. And this is 10 to the power 16 second. 10 to the power 16 seconds. So these are the characteristic time on the scale of which these interactions takes place. As far as exchange particle or mediator is concerned, mediators, here these are pions. In case of a strong interaction, these are pions and gluons. You can also write it as gluons. In case of electromagnetic interaction, these particles are photons. In case of weak interaction, they are heavy bosons and Z0. And in case of gravitational, this is graviton. So these are, so basically in this table we have summarized all the important characteristic parameters of these interactions. So this is all about these fundamental interaction, 4 type of fundamental interaction.